Okay, hi everyone. I just saw you in class. Sleepy, sleepy first period. Okay, here was the question that I gave you in class, the system. It was right here, and we just kind of talked through it in class. But let's just do it out together and see what we were kind of referring to, because I think we kind of got squished for time. We started getting a little bit. I know I started going a little bit quickly. So I gave you this system, and I said solve for A, B, C, and D. Now look what I did. Okay, I know that this here, this matrix, this is a 2 by 2, and this is a 2 by 2, and I know that the product is going to be a 2 by 2. So I used the column method. So I want your eye to just kind of look right here for a second, okay? I called the 2 by 2, that is the result of the left-hand side, right here. And I kind of thought of 2 by 2 as just two columns right here, okay? And like I said, I find myself using the column method. I think it's just, I find it just easier, and there's just less stuff to write down, and it gets less messy. All right, so the first column of the product is going to be the first column of the right-hand side multiplied by the columns of the left. So you see B plus 4 times 3 negative 6, C minus 1 here times 2A and 1. And here's the result of column 1. And I just plop that into column 1 here. Okay, and then column 2 of the product matrix is just right here. Okay, 11 and 5, 11 times column 1 right here, 5 times column 2, which is right here, and then I multiplied, so here's column 2. And then we can't forget about the right hand side, which is kind of waiting for us to finish the work on the left. And here is the right-hand side, okay? And probably, some of you probably are doing this with me and foresee already a problem, and we'll talk about that in a second. So then what Nick was saying is once you have a 2 by 2 equals a 2 by 2, you know that corresponding positions, if two matrices are equal, then corresponding positions have to be equal, right? Like these entries have to be equal, right here. Okay, and then when I do that, what I've got here is this system. So now I might go down to this system. And what I said was at this point, we'd have a system and we can use row elimination. However, hopefully your eye was drawn to this term right here, okay? The problem here is that this system is not a linear system. It's not a linear system. It's not a linear system, so row ops are out, right? Using the row operations to get to reduced row echelon form, that is a method only usable for linear systems. Okay, and I'm just going to do this and just say to you at this point, because this system is not linear, I'm not going to bother going through how you solve this, because we will not encounter situations like this where we will have a non-linear system. But my point is, now you know how to solve questions that look like this. And I think if you remember, I just kind of made this up on the fly. Reason number 100, I'm reminded to myself that why it is in linear algebra, I just can't make things up because they just don't work out that nicely. Okay, last little vocabulary word for today is, if you just go to the second page of your notes there, you'll see the transpose of a matrix, okay? And you'll see some notation that if you are given a matrix A, and oftentimes they'll kind of denote a matrix, they'll call it matrix A or matrix B, and usually a capital letter is used. Notationally, if you're asked for the transpose of a matrix, you'll see A with a superscript T, or I think I wrote down, you may see sometimes it'll have like the matrix symbol and the transpose of A, okay? Here is what the transpose of a matrix is. In shorthand, the transpose takes columns and makes them into rows and turns rows into columns. So notice here that in matrix A, row 1 is 2, 7. That row 1 becomes, in the transpose, column 1. Okay? Negative 1, 0 becomes column 2. 3, 3 becomes column 3. All right? So in a transpose, rows becomes columns. Columns become rows. Okay, that's what a transpose is. Some interesting things, some interesting little tidbits is this, and the whole world of matrices is kind of fascinating once you get into, once we get past this initial stuff. We're only kind of in our first couple of days of the course, but what's interesting is some interesting little patterns happen. Transpose of a square matrix and transpose of a square matrix. Oh my goodness. Transpose of a square matrix. And in case you're wondering what a square matrix is, a square matrix is just a matrix where the number of rows equals the number of columns, hence the name square. So let me show you something. Let's see, before I tell you what happens, let me give you the square matrix here. 2, 1, 4, 3, -7, 8, 0, -2, 22, 1, 5, 9, -11, 3, 6, 1. Okay, so this is a 4 by 4 square matrix. Okay, and I'll just call this matrix A. Go ahead and find the transpose of this square matrix and let me know if you observe anything peculiar. So pause me here for 2 little seconds and then let me know if you see anything peculiar. Okay, here's transpose. What's really kind of cool about transposes of square matrices is this. Look at the main diagonal. When you transpose a square matrix, the main diagonal stays the same. That's called the main diagonal. Okay, the main diagonal of a matrix is the main diagonal of a square matrix, I should say. It goes from top left to bottom right. But what's interesting is in a square matrix, the main diagonal stays the same. And also, do you notice this little property here? Look what happens. What happens is terms reflect over the diagonal. Do you see that? It's kind of neat, see? So when you see, if you look at the positions here, they reflect over the diagonal. So that's what I mean. I mean, we're kind of getting into the part of, at least initially, of matrix arithmetic that kind of you start to observe some cool things. There's other things we can kind of think about too. What do you think is the case for any matrix times the transpose? A times the transpose, do you think it will always result in a square matrix? Yes, no, what do you think? Right, will A times the transpose of A always result in a square matrix? You can think about it for a little bit. You can just do a little bit of playing around or doodling around with your finger or your pencil, but the answer here is yes. Okay. Okay, so that's all you need. So now you are all set to do your homework for this, and we'll continue with kind of getting the little foundational bricks of matrix operations and linear systems when I see you tomorrow. Goodbye.